Then we write m dB dt plus a friction term which we assume is proportional to v. This should be equal to the force F of t. And this is friction, which is F equal to ma with the friction term. And gamma is the coefficient describing friction. The thing that makes it different is that f of t is not an ordinary function. It fluctuates a lot. So f of t is not a function that you can specify at time t. F of t belongs to an ensemble. A statistical ensemble like this. Maybe as time goes on, maybe one of them looks like this. The next one looks like this. The next one looks like this. They're all different. But F is just to be averaged over all these ensembles. And that makes this equation a stochastic equation. Because in principle, you just take one of these and solve the equation, and you take another one and solve it, and you average everything. So that V is not a given variable, it's an average over the solutions over the entire ensemble. And so the only thing that is relevant here is a calculation of correlation functions. We just calculate correlation function. And we'll do that next time. This equation has an electrical analog. In a circuit. This you can write L di dt plus Ri is equal to V of t, where L is the inductance, I is the current, R is the resistance. And this describes the fluctuation of the current in a circuit due to fluctuations of the voltage, which fluctuates because of the Nyquist theorem. By the way, as a experimental fact, the fluctuation of the voltage on an average resistor is of the order of microvolts. So it's very small. Now, but how do you describe this ensemble? The ensemble is described by the correlation function between f's. F is defined only by the fact that F average of the ensemble is equal to 0. If you take the average over the ensemble, it's 0. But the correlation is not 0. F of t and t prime average over the ensemble is equal to this. It's at this point that we specify the model. We assume that it's equal to some constant times the delta function t minus t prime. That is, the correlation is a very short time. Now, in Brownian motion, this correlation time should be of the order of molecular time, 10 to the minus 20th second. We assume that it's 0. We ignore it. So we have a delta function. That there's no correlation except when they are right at the same time. And this is called white noise. The correlation that vanishes except when they are equal, that's called white noise. That means, later you might see that means that all Fourier transforms of the energy are equally important. So we have a model of this. So this is what specifies our model, and this is the step in which you insert this assumption that there is no memory. How do you solve this? It's very easy to solve this. That's the advantage of Langevin. You can solve it instantly by the technique of Fourier transform. So you write v of t is equal to integral d omega over 2 pi e to the minus I omega t times v sub omega, this is Fourier transform. And f of t is equal to integral d omega over 2 pi minus e to the minus I omega t times f sub omega. Now, if you translate this definition into Fourier transform, you will find that f omega times f omega prime. Oh, by the way, before I do that, v and f are physical quantities. Of course, they're real. But the Fourier transforms are not real because of e to the minus I omega t. But because they are real, you have v omega star is equal to v of minus omega, and f omega star is equal to f of minus omega. And these comes from the fact that in ordinary space they are real. And now if you, in terms of the Fourier transform, you can verify this is just equal to 2 pi c0 delta plus. If you want a minus, you have to put a star there. And now with this, we can solve the entire problem. It's completely solved. Because now I take the Fourier transform of the Langevin equation on both sides. You see, for example, dv dt, which I need in the first term there, would be equal to d dt of integral d omega over 2 pi e to the minus I omega t v of omega. And this dt only acts on this because the rest is independent of time, so I just get integral d omega over 2 pi times e to the minus omega t multiplied by I omega. So d dt is the equivalent of multiplication by minus I omega. And if you use this throughout the terms, the equation, the Langevin equation, becomes minus I m omega b omega plus gamma b omega is equal to f of omega. And therefore, you can solve for the Fourier transform for v omega is equal to f of omega over m times 1 over gamma minus I omega. And this is a solution. And we can now use this to calculate correlation functions. Now, this is so simple because on the right side, we only have a random force. If I add a regular force, you may not be able to solve it. But this is just a free particle in Brownian motion. Now, let's now compute some correlation function. This is the solution to that equation. You can take the inverse. You can take v of t, which is equal to integral dt minus e to I omega t v of omega, d omega. Sorry. V of t is equal to d omega. Yeah, this is 2 pi here. There was no 2 pi over there. I think I was wrong. There was no 2 pi here. Yeah, this. Oh, yeah, this is right. Yeah. So now if I stuck in the v omega t, so it'll be equal to minus infinity plus infinity d omega over 2 pi e to the minus I omega t times f of omega over m times 1 over gamma minus I omega. This is a solution, except that f of omega is a random function. So again, you have to consider correlation functions. You can solve this in the computer though. You have an ensemble and solve for each Fourier component for each f, and then you average the result. In the computer, you will solve each case and you average the result. And then in that case, the problem is how to generate this ensemble so as to satisfy the white noise condition. Now let's calculate some correlation functions. Well, first of all, let us relate of this gamma to mobility. We're going to use this later. Suppose for the moment the external force is equal to F external plus F random. So far we have ignored this term. Suppose now you ignore this term, just take a consider it's just an external force. Then the terminal velocity is obtained by this one dv dt is equal to 0, right? When you plug it into the Langevin equation, you will find that how do you write m you will find that m gamma u is equal to F external. This dv is 0, and therefore this by definition is equal to 1 over the mobility, because u is eta times F, and therefore the mobility F is 1 over m gamma. Let us now calculate V omega star, V omega prime average. Using the solution there, I get 1 over m squared times F omega star, F omega thing average divided by gamma plus I omega, gamma minus I omega prime, and I get 1 over m squared times delta of omega minus omega prime. This is 2 pi c divided by gamma squared plus omega squared. Minus plus. So, and this comes from this. So it means that the correlation is equal to this, and the coefficient. Let me write it. This is equal to this by definition S of omega times 2 pi delta omega minus omega. The delta always equal to 2 pi, and this the S is called the power spectrum. C0 divided by m squared gamma squared plus omega squared. This is a power spectrum. Why is it called a power spectrum? Because if you integrate both sides over omega prime, on this side you will get omega square star integral v omega prime. On the other side you would get s omega times 2 pi. And this is equal to omega at t equal to 0. So this becomes omega star. That integral becomes v at time t0 is equal to 2 pi s of omega. And I'm now integrate both sides with respect to omega. Say v of t, v of 0, say, this is equal to some constant times integral d omega s of omega. This leads to this. And this shows that the there's a e to the minus I omega t here. So therefore v0 squared average is equal to some constant times integral d omega s of omega. And this side is the kinetic energy. So the kinetic energy has been decomposed into different frequency components. That's why S is called as power spectrum. This is just an aside, but the main result is that the power spectrum is obtained from the correlation between velocities. Now let us consider how the energy, let's consider energy balance in the Brownian motion. You take the equation m dv dt plus m omega v is equal to f. You multiply both sides by v, and you take the average. But this can be written as m over 2 d2 dv squared dt plus m gamma v squared is equal to Vf. This is the kinetic energy. So if I take the average, I get d dt of the average of mv squared over 2 plus m gamma v squared is equal to Vf. This is the kinetic energy, called as K. Therefore dk dt is equal to Vf minus 2. Okay. And this is the work done on the particle by the medium. F is a force acting on it, as V times F is the work done on the particle. This term is the dissipation. So this says that here's the medium. at temperature T, the particle is immersed in this medium and it exchanges energy with this medium. It gives energy to this medium through dissipation. It's 2 gamma k. And it receives energy from the work through Vf. And in equilibrium, these two balance. dk dt is 0. So in equilibrium, two gamma k must be equal to Vf. That is, the work done on the particle must be equal to the dissipation. And we're going to work this out a little bit, and we'll say that this is the dissipation, fluctuation dissipation theorem. This is fluctuation, this is dissipation. To work this out, we have to calculate Vf average. So to find AVF, to calculate this average, you go back to the equation m dv dt plus m comma v is equal to f. And you let v equal to, say, e to, we're going to remove this term, so it's e to the minus gamma t times f times u. And then m du dt is equal to e to the gamma t times f. And this term can be integrated. Therefore, u is equal to 1 over u of, this is a function of t, is equal to 1 over m times integral 0 to t dt prime e to the gamma t prime times f of t prime. On the other hand, v of t using that definition is just 1 over m 0 to t dt prime. I just take gamma t prime minus t times f of t prime. So I have a solution of v of t. Now just multiply by f. Therefore, v times f on the average is equal to multiplying both sides by f. I get 1 over m 0 to t dt prime e to the gamma t prime minus t times f of t prime, say f of say 0. I multiply both sides by f at time t equal to 0. And this is equal to c0 times delta of t prime. As a result, I find that Vf is just equal to C0 over m. And therefore, dk dt finally is equal to C0 over 2m minus 2 gamma k. You can now solve this equation and find that k of t, the kinetic energy, is equal to C0 over 4 pi gamma times 1 minus e to the minus 2 gamma t. As time goes on, this term decays, and this is the term at time infinity. The t at infinity is equal to z0 over 4 pi gamma. And this is the equilibrium value for it, and infinity this goes to 0 because it goes to a constant. So substituting into our previous statement, you will find that Z0 2m is equal to gamma kBt. And this is fluctuation dissipation theorem. We derive this way. And this shows again that, again, if this is a medium at temperature T, this particle, it gives energy and it receives energy, and these two balance. It gives amount of energy kT, gamma kBt, receives energy Z0 over 2m. And these two balance, and that's the fluctuation dissipation theorem. From this you can see that the fluctuation dissipation theorem is a result of equilibrium. Because if the system is not in equilibrium, these two terms are not equal. And in practice, there are systems in which this theorem is violated. In a glass, for example, this is generally violated because a glass is it looks like solid, but it's a fluid. It slowly flows, and it takes hundreds of years to reach equilibrium. And in such cases, this theorem is violated. An interesting case that I used to live in Boston. In Boston, there's an old section called Beacon Hill, in which the houses were built from the 17th century. And they were built with glass windows. You look at it, the windows become thickened at the bottom because the gas flows. So the window pane, if you look at the side, it was like this. Now it looks like this. The glass just flows, and it has not yet reached equilibrium in 300 years. In fact, the deviation from this theorem in glass is a topic for research. Now I'd like to introduce a method that will illustrate more this connection, that this is fluctuation, we say, because it's related to the force. But we would like to see this expressed in terms of a correlation function, to really look at the correlation. To do that, we need a theorem that relates the power spectrum to correlation function. Consider the correlation that we have computed. This is equal to, let it put in the correlation. You have dt minus 1 plus infinity e to the I omega t v of t. This is the first term. The second term will be integral from minus dt prime, say, e to the minus this is omega prime t prime v of t prime, average. This is equal to integral dt prime rho from minus 1 plus infinity e to the minus I omega t plus I omega prime t prime, the correlation of Vt and Vt prime. But we know that this is equal to S of omega times 2 pi delta function omega minus omega prime. We know this. And therefore, this integral must be equal to this. In order to do that, we just integrate both sides. On this side, the integral just cancels out this delta function. On the other side, we just integrate over W prime. So let me just try to do it here. On the left side, I just get S of omega times 2 pi. Because the integral over the delta function is this equal to. Here I just have dt e to the I omega t. This is untouched because I'm integrating to delta prime. Here I have dt prime e to the minus I omega t. And now I have integral d omega prime e to the I omega prime of t prime times vt prime. Oh, you know what this integral is. That's the delta function. This is equal to 2 pi times delta function in t prime. So now I can do the t prime integral on the right-hand side trivially. So this is equal to 2 pi delta function t prime. So I just set t prime equal to 0 to do the integral, right? So the result is integral dt e to the minus I omega t times v of t, v of 0 is equal to S of omega. That's a very interesting result. This is called the Wiener Kinking theorem. Kinking theorem. I don't know why it's called a theorem because it's so trivial. I think it's because when they derive it, they did not use the delta function. And if you do not use the delta function, you have trouble deriving this. Very complicated. But mathematicians think that that's not rigorous, so it's this step. So this was a delta function. What does this say? This says that this is a fluctuation. If you take a Fourier transform, it gives you a power spectrum. And the Fourier transform is this prism. On this side, you have a wave coming in. And this has a correlation at 2 points, this point and this point, at time t equal to 0 at time t. Because at time t, this point has moved to here. So this thing is a correlation between 2 points on the wave. And this, through this particle, becomes a power spectrum. It gives you the power into each Fourier component. And so that's a very interesting theorem. It says that Fourier transform is a prism. It analyzes correlation into this power, the intensity of each Fourier component. Another way of re-expressing the Wiener Kinking theorem, usually it's stated in a real form. So usually you reduce it as follows. You say that S of omega is equal to, you write 0 to infinity dt e to the minus omega t v of t v of 0 average, and you plus that other term 0 minus 1 to 0 dot e to the minus I omega t v of t v of 0, and in this term you let t go into minus t as a substitution. So then this term becomes integral from 0 to infinity dt e to the I omega t of v of minus t v of 0. And then you say that this, of course, is equal to v of t v of 0 because of time reversal invariance. And as a result, you get this is equal to integral 0 to infinity dt e to the minus I omega t plus e to the I omega t v of t v of 0. And so it is equal to, so you could S of omega is equal to 2 integral from 0 to infinity dt v of t v of 0 average times cosine of omega t. This is usually how the theorem is stated. So it's again, a relation between correlation and power spectrum. So now let's go back. The power spectrum, we have derived it to be C0 over m squared times 1 over omega squared plus gamma squared. And using the Wiener-Kinking theorem, this should be equal to 2, 0 to infinity dt vt v0 cosine omega t. Set omega to 0 in this case. Then you see that on this side you have C0 over m squared, m0 m squared gamma squared is equal to 2 integral dt v of t v0. The cosine is 1. And remember the connection between gamma and the mobility. You get dt v of t v of 0. If you integrate this from 0 to infinity, you get gamma of kbt. And this is another form of the fluctuation dissipation theorem, which really shows you that it's a fluctuation. It's a correlation with a fluctuation. So again, this is a fluctuation dissipation. In a more explicit form. Here's a dissipation, here's a fluctuation, which knows a correlation. See, when we did Einstein's derivation, we derived this, and we also derived Einstein's relation, the relation between diffusion and the mobility. How do we do it here? Let's do it in this context. To do this, you need to calculate the diffusion coefficient. You try to calculate the diffusion coefficient. D. And here we do it by relying on the fact that we will say that dx is a stochastic variable. And therefore obeys Gaussian distribution by the central limit theorem. With a variance involving d. D is defined by that variance. With a variance it's 2 dt. Right? So all we need to do is to calculate the variance. So we shall calculate the variance. Which is x squared average. We can do that because that's a correlation function. If we go back to the equation, m, instead of dvt, we know as a d2x dt squared plus m gamma, instead of v, we write dx dt is equal to f. And I'll multiply both sides by x. Now we can show, which I will not do here, that fx average is equal to 0. It's sort of reasonable. But this can be shown by a more detailed calculation, but I will not show it here. I'll just state it. And therefore this average on this side is 0. That is m. Let us say x times d2x dt. We have this term. This is equal to 1/2 second derivative of x squared minus dx dt squared. This is just simple differentiation relation. And therefore on this side we have 1/2 dt squared, I average x squared, minus 1/2 m gamma dt x squared is equal to minus dx dt squared average is equal to 0. And this term is the average of v squared. And we know that to be c squared over 2m squared gamma 1 minus e to the minus 2 gamma t. We have solved the kinetic energy earlier, right? Recall that the kinetic energy is equal to 1/2 mv squared. We have solved this into and this we can drop if time is long enough. And therefore x squared is equal to C0t over m squared gamma squared. And therefore, that's the variance. You set it equal to the diffusion constant, 2 dt. Therefore, you get d is equal to kBt eta. That's Einstein's relation. And that relates to this. So this illustrates how you can get everything from the simple treatment by this more formal treatment. And you can extend this to other cases. Now, it's an interesting thing that that the solution of this equation gives you random walk. So as an end to this, let me just mention some applications that I'm personally involved with. You have the Langevin equation, m dv dt plus m gamma v is equal to f random, which is important, plus g, say, g is a regular force. G is a regular force. Say g, for example, g is going to minus some gradient. G is a regular force. If you turn on the g, sometimes you cannot solve this equation. We solve it by taking Fourier transform. But maybe g is very complicated. You cannot take the Fourier transform. So how do you address that? You can solve it on the computer. You can say that this part, without the g, this part gives you a random walk. This part gives you the x, the position just exhibits a random walk like Brian Ocean. And this picks out from the random walk a subset. This gives you conditioned random walk. So in random walk, you take a step, either this way or this way, and the probability is the same. Say P and Q probability. P is equal to Q for random walk. If you just take a point here and throw a coin or generate random in computer, just make displacement either back and forth. If you do it long enough, you get diffusion. You solve this equation. If you have this term, maybe you cannot solve it analytically, but you can do it on the computer. You can make P not equal to Q by weighting it with this G. And that's called conditioned random walk. Now, how do you weigh it? You weigh it by considering what you want to do when you solve this equation. As we said, this is a stochastic equation. And you have an ensemble of states. You do not have one state, you have an ensemble of states. The states are an ensemble. And therefore, what you want to deduce from this equation on a computer is to generate configurations one after the other that generates the ensemble. So suppose C is a state of the system. you try to generate an ensemble. C1 going to C2, going to C3, and so forth. You have some updating algorithm that will generate this ensemble. If you generate it long enough, that's an ensemble. You're going to take average, just average over these states. And that ensemble is existing in your computer, in the memory. You can do anything with it once you get an ensemble. So the trick is to find the algorithm that updates the state from one state to the next. With the Langevin equation, the updating algorithm was just random walk, just P equal to Q. But with a G, you have to weight it. You have to generate an ensemble with a weight. How do you do that? The general method is called the Monte Carlo method. The Monte Carlo method is a method to update the system such that eventually it produces a canonical ensemble with KT. That is, if you wait long enough after it's warmed up, all the states thereafter will distribute according to a canonical ensemble. So you take average after that, you average over a canonical ensemble. How do you do this? There's a very neat algorithm called the Metropolis Algorithm. You must know this. Metropolis. First, let EC be the energy of state C. To update, you first generate a state at random. Generate a state C1 at random. Suppose you want to update C0. You first generate a state C1 at random. Then you compute the energy of C1 minus energy of C0. Delta E. The algorithm is, if delta E is less than 0, accept. If it lowers the energy, you accept it. That's very natural, right? The crucial thing is that, however, if delta E is greater than 0, you still accept it. That's the crucial point. You accept with probability e to the minus delta E, the Boltzmann factor. And this simulates the thermal fluctuation. So you generate a state, even if the energy goes up, you might still accept it. And that's the thermal fluctuation. With this algorithm, you can prove that eventually you have a canonical ensemble. And to include G, you include G into the definition of E. And that's how you can solve such an equation on a computer. I have applied this to a model of protein folding. You take a protein as a chain, as a long chain molecule. It's not a particle, it's a chain. You put it into water, and it performs Brownian motion. And that will satisfy some equation like this, except this G has to do with the attraction between different parts of this chain. You put it in, and you have a computer algorithm for protein folding. So you put it in, you do the algorithm, and the thing folds. I was playing with that for a while. But it was a very interesting model that you can try other things too. And this would conclude the course. Thank you.